Welcome back. In today's video, we will solve some important previous year GATE questions on linear algebra. These questions will cover various topics like change of bases, dimension of subspaces, linearity, etc. If my videos are helping you understand these concepts, please give them a thumbs up, subscribe to the channel, and share with others who might benefit. So let's get started. So here is question LA15 on your screen. So it says let T be a linear transformation from R3 to R2 defined by this. Then the matrix of T with respect to the ordered basis this and this is. Okay. So first of all, this question is on the topic change of basis, which we discussed in the previous lecture. So if you haven't watched that video, then I highly recommend watching it because if you have clarity on that concept, then this question is easy for you. Okay. So first of all, this is a linear transformation and we are moving from R3 to R2. All right. We are moving from R3 to R2. So we know that this belong to input vector space and this is output vector space, right? This is input vector space and this is output vector space. Okay, so that means our input vector v, let us suppose v is our input vector, it belong to r cube, and t times v, which is the transformed vector, which is the output vector, it belong to r2. So let A is the matrix corresponding to this linear transformation. All right. So what is the shape of A? What is the shape of A? So the shape of A is 2 cross 3. Why? Because we already know that this is the second term is it belongs to the vector coming from the input vector space, and the first term belongs to the vector coming from the output vector space. And we already know that input vector space is R3 and output vector space is R2. So A is nothing but a 2 cross 3 matrix. A 2 cross 3 matrix. So there are three column vectors. There are three column vector. This is the first column vector, this is the second column vector, and this is the third column vector. All right. And if you have seen my videos, I have already told you many times that column vector is nothing but where the basis vectors land. Okay. So what this represents, this is nothing but where first basis vector land, where the first basis vector landed. Okay. And we know that the input vector space is R3. We know that the input vector space is R3. And for R3, the length of basis set is 3, right? The length of basis set is 3. That is, we need minimum 3 linearly independent vector to span the entire R3. So therefore, there are 3 column vectors. And therefore, these 3 column vectors represent where those 3 vectors belonging to the basis set lands. Okay, so here this is where the first basis vector landed, this is where the second basis vector landed, and this is where the third basis vector landed. All right, now if you see, this is a non-square matrix. I have already created a video on non-square matrix where I explained that what non-square matrix do. They move vector from one dimension to another dimension. So in this case, the input vector belong to R3, that is, it belong to the three-dimensional three-dimensional volume, and it got transformed to R2, that is the our XY plane, right? So for example, okay, for example, this is x-axis, this is y-axis, and this is z-axis. We know our standard basis set for R3. It is I hat, j hat, and k hat, right? And our transformation T is transforming it to R2, right? It is transforming it to R2. Here is x-axis and here is y-axis. And we know the standard basis set for R2 is I hat and j hat, right? Okay. So a three-dimensional vector, some three-dimensional vector is getting transformed to this to a two-dimensional vector using this transformation T, right? Okay. So if these are the basis set for input vector space and output vector space, then the first column vector is where I had landed, the second column vector is where j had landed, and the third column vector is where k had landed. Okay, but there is a twist. There is a twist. They said that we need to give the matrix representation of T with respect to these ordered bases. This is the first ordered basis. This is for the input vector space, and this is for the output vector space. Because we are moving from R3 to R2, and in R3, the basis, the dimension of R3 or the length of the basis set is 3. Therefore, there are 3 vectors in the basis set for R3. And for R2, we only need 2 vectors. We only need 2 linearly independent vectors to span the entire R2. Therefore, the basis set for R2 contain only 2 vectors, right? So now, because this is the basis set, we are no more considering I hat, j hat, k hat. What is the new basis set? The new basis set is, this is the new basis set for R3, 1 1 1. So I think maybe 1 1 1 is some lying somewhere here. That is 1 1 1. So this is the new basis set. Second is 1 minus 1 0. So 1 minus 1 0 is somewhere here. 1 minus 1 0. So sorry, here, right? This is 1 minus 1 0. All right. And the third one is 0 1 0. 0 1 0 is j hat itself, that is here. 0 1 0. Okay, so now the basis vector for R3 is this one. Let us suppose we call it uh, E1, or let us suppose B1. Okay, so the first basis vector is 1 comma 1 comma 1. The second basis vector is 1 comma minus 1 comma 0, and the third basis vector is 0 comma 1 comma 0. It is no more I hat, j hat, k hat. Okay, if it is no more I hat, j hat, k hat, then we cannot represent any vector using I hat, j hat, k hat. Similarly for R2, the output vector space, the basis set is not I hat, j hat. It is 1 comma 1, which is here. Okay, 1 comma 1, and it is 1 comma 0, that is this j, 1 comma 0. So let us suppose this is E1, and let us suppose this is E2. All right, so let us this is B1, this is B2, and this is B3. I am adding this hat just to distinguish that these are not normal vector, but these are basis vectors. Okay, so this is a basis vector. All right, so similarly the basis vector for the output vector space, that is R2, is E1 hat, which is 1 comma 1, and E2 hat, which is 1 comma 0. All right, now because we need to find this matrix A, which is the matrix representation of linear transformation T. So basically all we need to find is where the first basis vector landed, where the second basis vector landed, where the third basis vector landed. So these are the 3 basis vectors. We need to find where this basis vector B1 land after transformation T, and we know that T is a linear transformation. So all we need to do is we just simply need to transform the first basis vector, that is B1 hat. And what is B1 hat? It is 1 comma 1 comma 1, and we are already given this transformation. This is the transformation that T x y z is x plus y and y minus z. Okay, T x y z is x plus y and y minus z. So using this formula, we will transform B1 hat, B2 hat, and B3 hat. Okay, so it is given x plus y, y minus z. So if I put that x plus 1 and y minus z, I will get 2 comma 0. Similarly for B2 hat, what is B2 hat? It is 1 minus 1 comma 0. So x plus y is 0, and y minus z is minus 1. All right. Similarly for the third basis vector B3 hat, this is, what is B3 hat? 0 1 0. So this is 1 comma 1. All right. Now 99% of a student will make a mistake here. They will simply say that A, the matrix representation for this transformation is this, is A, that is 2 comma 0, 0 comma minus 1 and 1 comma 1. That is where I had landed, sorry, B1 had landed, B2 had landed, and B3 had landed. But this is completely wrong. 99% student will make this mistake. So here where your concepts came into picture. See, these 2 comma 0 0 comma minus 1 1 comma 1, these vectors are with respect to this I hat and j hat. Okay, but not only the basis set for input vector space is changed, but the basis set for the output vector space is also changed, right? They give us basis set for both input and output vector space. So we need to further transform these vectors. Why? Because these are not according to E1 hat and E2 hat. No, these are not according to E1 hat and E2 hat. These are according to I hat and J hat. But the output vector space has different basis set, that is 1 comma 1 and 1 comma 0. So we further need to convert these according to this E1 hat and E2 hat. All right. So 2 comma 0, how can 2 comma 0 can be written as a linear combination of E1 hat and E2 hat? Simple. It is nothing but 0 times E1 hat plus 2 times E2 hat. I mean, if you simply multiply 0 with the first vector and 2 times with the second vector, you will get 2 comma 0, right? Similarly, for the second one, it is minus 1 times E1 hat plus 1 times E2 hat. So minus 1, 1 comma 1 plus 1 comma 0. So you might be thinking that how I am able to get this combination, right? How I am able to get this combination. So because like it's pretty simple, right? Here we need 2 comma 0. Here we need 2 comma 0 and we already know that E2 is 1 comma 0. So this 2 comma 0 is nothing but a scaled version of E2. So E1 will contribute nothing. So that's why its contribution is 0. That's why its contribution is 0. Whereas because E2 this T times B1 hat is nothing but 2 times E2, so I have taken 2 here. So similarly, I mean you need to put some effort, but yeah, you will easily get this linear combination. Similarly, if you need to produce 1 comma 1 using this, see this is also simple, right? If you need to produce 1 comma 1, E1 is already 1 comma 1. So if E1 is already 1 comma 1, then you just need E1 and E2's contribution will be 0, right? So this is 1 comma 1. Okay, so basically now these vectors 2 comma 0 0 comma minus 1, these are according to the standard I hat and j hat, but because the output basis set is already changed, it is no more I hat j hat, it is 1 comma 1 and 1 comma 0. So we need to change them for transform these further according to these basis vectors. So we get 2 comma 0 0 comma minus 1 and 1 comma 1. So therefore the matrix representation of T, which is A, is this, where the first basis vector landed, where it landed at 2 comma 0, but 2 comma 0 is represented using this E1 hat and E2 hat as this 0 2, that is 0 times the first what do you say, the first basis vector and 2 times the second basis vector, so 0 2. Similarly, the second basis vector is minus 1 1, and the third one is 1 times 1 and 0. Okay, so I will just highlight this. So this is 0 2, that is the first one, minus 1 1, that is the second column vector, and third is 1 0, that is the third column vector. So yeah, that's all for this question. So let's see LA question 16. So this question is on dimension of subspaces. So we are given two subspaces W1 and W2, and the W1 subspace, the vector belonging to W1 subspace are four-dimensional, same for W2 subspace, but there are some restrictions given. So W1 subspace has two linearly independent restriction and W2 has only one. So as you have seen my previous videos on LA questions, I have told you that dimension of a subspace. So dimension of a subspace, let's say W1, is first of all the dimension of the vector space to which the vector belongs. So here the vector belonging to W1 is four dimensional. So 4 minus the number of linearly independent restrictions. So these are restrictions, right? We restricted something. So this z plus w equal to 0 is nothing but these are planes. The z plus w equal to 0, right? So these are restrictions, and both of them, that is x plus y plus z equal to 0. This is the first one, and z plus w equal to 0. So these are linearly independent, right? These are linearly independent equations. So there are two linearly independent restrictions. So the dimension of W1 is 4 minus 2, that is 2. Similarly, the dimension of W2 is 4 minus 1. There is only one linearly independent restriction, so it is 3. Now, in the question, it is asked the dimension of W1 intersection W2 and W1 plus W2. All right. So we already know the formula for sum of subspaces, dimension of sum of subspaces, but there is as such no formula for this intersection. But there is a way to calculate dimension of intersection of subspaces. So for example, we need to calculate the dimension uh, of W1 intersection W2. So uh, when W1 and W2 are these subspaces, so basically because W1 and W2 belong to R4, so their intersection will also belong to R4. Basically, we need four values to represent a vector belonging to the intersection. So it is 4, right, as we did in this case. But here the number of linearly independent restrictions. Okay, so now we basically need to subtract the total number of linearly independent restriction in both W1 and W2. So in W1 we have two linearly independent restrictions, whereas in W2 we have only one. So we need to add, and we will get the total linearly independent restriction, which is 3. So in this case it is 4 minus 3 equal to 1. So this is the dimension. This is the dimension of W1 intersection W2. So the process is same. We first write down the dimension of the vector space, original vector space. In this case, it is 4, right? Then we subtract the number of linearly independent restrictions. In case of intersection, we need to first sum all the linearly independent restriction for both the subspaces. Now the dimension of sum is pretty straightforward. We have a formula for that. The dimension of W1 plus W2 is dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2, right? So this is 2, this is 3, and this is 1. So the dimension of W1 plus W2 is 4. So therefore option A and C are correct. Option A and option A and B are correct. All right. Option A and B are correct. So let's see question LA17. It is given that consider a vector space R3 and the map f and g from R3 to R3. So f and g are linear transformation. No, sorry, they are not linear transformation. They are mapping from R3 to R3, and they are defined as this. So we need to find whether these maps, these transformations are linear or not. So these are the transformations f and g given like this, and we need to find if these transformation are linear or not. Transformation and maps are the same thing. Okay, so let's first find for f. Okay, so first of all, a map or a transformation is linear if and only if it satisfies the linearity property. What is the linearity property says? It says that uh, if this is the f function, then f of a times the first vector, let us suppose it is x1 y1 z1, because it's a R3 to R3 map, so we need to take a three-dimensional vector, plus b times the second vector x2 y2 z2 should be a times f of x1 plus y1 f of x1 y1 z1 plus b times f of x2 y2 z2, right? So basically it is saying that f of a times v plus b times w is equal to a times f of v plus b times f of w. Okay, this is the same thing. So we need to check this. So what is f? F is f of xyz is x, y mod and z. So we need to check this property. If this is holding, then f is a linear map. So what is f of a times the first vector, that is x1 y1 z1, plus b times the second vector x2 y2 and z2. Okay, what is this? So we can basically expand the inner term. So this basically becomes ax1 plus bx2, ay1 plus by2, az1 plus bz2, right? I just expanded this. So this is a times this vector is nothing but scalar vector multiplication, and I am doing after that I am doing vector addition. Okay, so I get this. Now what is f of xyz? It is x, y mod and z. So I can write this as, can simply write this as a times x1 plus b times x2. The second term is will be mod of a times y1 plus b times y2, and the third term will be a times z1 plus b times z2. So this is our left hand side, right? This is our left hand side. Now we need to check what is the right hand side. We need to check the right hand side. So right hand side is a times f of x1 y1 z1 plus b times f of x2 y2 z2, right? So what is x1 y1 z1? It is x1 y1 mod z1 plus b times x2 y2 mod z2, right? So this is nothing but, if I do this scalar multiplication and then addition, so this will be a times x1 plus b times x2, a times y1 mod plus b times y2 mod, a times z1 plus b times z2, right? Now are these two terms same, this one and this one? No. Why? Because the first in this three-dimensional vector, the first coordinate, the first value is same, ax1 b plus bx2. Even the third value is same, but the second value is not same. Why? Because a times y1 plus b times y2, mod of ay1 plus by2 is not equal to a times y1 mod plus b times y2 mod. So we know that mod of x plus y is not equal to mod of x plus mod of y. This is the from property of modulus, right? So therefore f is not a linear map. F is not a linear map. Now just like I checked for f, you can check for g also. So take it as a homework and let me know if g is linear or not in the comment below. All right. So that's all for this lecture. We have covered three very important questions, okay, on various topics. So if you find this video helpful, then like it and share with others. Also subscribe to the channel. Till then, thank you. Bye.